Bonjour et bienvenue au premier colloque des sciences mathématiques de l'année. Welcome to the first colloque des sciences mathématiques this year. Aujourd'hui, on a le plaisir de recevoir Eva Miranda. She's from the University Polytechnic Catalonia, and her research is in symplectic geometry, Poisson geometry, foliation theory, geometric quantization, and fluid dynamic and contact geometry. She also has a big outreach program, which you can find on her webpage. This is very interesting. But today she will speak on looking at hydrodynamics through a contact mirror from Euler to Turing and beyond. So Eva, the floor is yours. Thank you.
Thank you. Thank you very much for this invitation. C'est un plaisir d'être ici à Montréal, même si je suis à Barcelone. It's a pleasure for me to be there, even if virtually. And well, I mean, I have something in common. I'm in the other CRM, right? In the Centre de Recerca Mathématica in Catalonia. So there are some links. So thank you very much for this invitation. For me, it's like a pleasure to be speaking here. I'll try to make my best to try to motivate you to look at some of a recent program that I have with Daniel Peralta and some other collaborators. And what I'm going to describe is a connection between apparently two different worlds inside mathematics, which are like fluid dynamics and geometry. Like when we think of geometry, we think of straight lines, everything clear. And when we think of fluid dynamics, we think of turbulence and so on. And what I'm going to do is to construct a mirror between these two worlds, and I'm going to use it to solve problems in fluid dynamics going to geometry. That's a little bit. So I'm going to feel like this engraving here, which is an engraving of Alice in Wonderland. And, you know, I'm going to cross this mirror and try to see what I get from the other side. And, well, I'm going to try to motivate. It's like we are in the cinema now. And well, probably you don't remember this commercial because it's a commercial that it's from Europe, but I'm gonna put it anywhere because it explains a nice story. Huh? What's going on? Yeah.
On the 12th of January 1992, the merchant ship Old Susan, sailing the Hong Kong San Diego line, was caught in a terrible storm and lost all its cargo. 20,000 rubber ducks. Years and 6,000 miles later, the inhabitants of Stratford in Scotland woke up to the unusual sight of thousands of ducks invading their coastline. Life is full of surprising endings.
Well, this is a commercial of a car. And of course, they want you to buy the car. So they tell you that life is fantastic and full of fantastic endings. And who are the main characters of this ad are these small little ducks that I have of several colors. Why I have so many ducks at home, I don't know. But what this ad, this commercial is explaining is based on a true story. As everything in cinema is based on a true story, but there is a kind of distortion because it says that a lot of these ducks appeared in Scotland. But what happened is the following. So this commercial is based on a true story. And this story was so famous that these little ducks that were lost in a storm have a name and they are called the friendly floaties. And the true story is that in January in 92, there was a carrier having a lot of things on the cargo, but in particular, 29,000 rubber ducks and other animals, not necessarily ducks, but. And then in November, 10 of these ducks appeared in Alaska, in Sitka. And then they were expected, like, there was a program developed by two people in oceanography, which was predicting where these ducks would show up. And then it was advertised that in July 2007, many of these ducks would show up in Scotland. And indeed, that's the commercial is from 2006. It's a Seat Toledo, so not a good car to buy to have in Canada. You have better cars, but well, it tells us a lie. It tells us that all these DAGs appeared in Scotland, and indeed, the truth is that this was advertised in the news. They were expected all these DAGs to appear in Scotland, but the truth is that only one was originally from that cargo appeared in Scotland. So what did we learn from this accidental storm and this accidental loss of these DAGs? Well, the people who developed this program to know where the DAGs would be, they were indeed interested in the movement of not only lost DAGs, but movement of flotsam or icebergs or message bottles. Indeed, they made an experiment where they were throwing a lot of bottles with messages inside. And then the nice thing or the interesting data is that only 2% of the messages on the bottle were recovered. How did they know that? Because how maybe you get one of these bottles with a message and you don't inform Curtis Evans-Meyer. Well, they know it because they left a note inside saying that you will get $50. And then if you get such a note, then you try to get this $50. So based on this experiment, we could say that it was quite unpredictable to know where a message in a bottle would go. So in a way, all these, romantic stories around throwing a message inside a bottle, don't do it. Use WhatsApp because it's most likely this person will not get this message. So what I want a little bit today to explore is why it's unpredictable to know if the message will get there or not, and why these little DAGs didn't really show as it was predicted they would in Alaska in this commercial. And indeed, there is a true story. Curtis Evans-Meyer, indeed, he was an amateur initially, but he started to work with Jimmy Graham, and they even developed a computer simulator called OSCURS, Ocean Surface Current Simulation. And based on this current simulation, they could predict where the floats, what was the movement of the floats. I have to say that there is a hidden information here, which is that if we think that these DAGs are moving in 2 dimensions, then this program would work, because then this is an integrable problem. But if these DAGs move in 3 dimensions, then the message is that you can think that they move, that the movement is given by some Euler equations, okay, in dimension 3. And then we have a problem about how do you integrate this? How can you find the path of this little? Okay. Indeed, what's funny is that the fact that it's a 2 or a 3-dimensional problem is based on the fact that maybe your DAG has some of these DAGs do not have this little space here, and some have. So some of them have a hole. The ones that have a hole, their problem is 3-dimensional, and the ones that don't have a hole, it's 2-dimensional. Therefore, it's an integrable problem. Okay. So this is the true story. And this brings us to think that, this anecdote of the little DAGs makes us think that maybe fluids are more complicated than we think, okay? And this is something we see, right? We see every day, in the tsunamis or in big storms, or this is a picture taken in La Palma. We had several volcanoes in the world in September, indeed last September and August, several of them in Italy and Spain, that they started to spill lava, and we didn't know where this lava would go. Of course, lava has some viscosity. So then the kind of equations that model this fluid are going to be different than the ones of water, because viscosity is going to play a role. So in a way, what I want to analyze is the complexity of fluids, and based on this idea of nature. Indeed, this could take us to a film, which is Solaris, which is based on a novel. Well, the film has, I think, 4 different versions, and 2 in Russian and the most recent was by Soderbergh, I think. And well, in that field, there is a big sea, which is the thinking sea. And indeed, in the book, they talk about the thinking ocean. And in a way, they say that the thinking ocean of Solaris is a gigantic brain, prodigiously well developed, and millions years in advance of our civilization, a sort of sage symbol of omniscience, etc. Well, indeed, the film is a little bit then really science fiction because we talk about aliens and so on. But well, indeed, I learned about this thing after giving a colloquium talk in Madrid. Somebody told me, look at this, Solaris. So somehow we could think that we are close to science fiction, but no, we are talking about science. Indeed, it was Cris Moore who asked if fluids are complicated enough to create a fluid computer. And this a little bit connects with an old program by Penrose, okay, talking about what are the limits of computation. Okay, so here we have Penrose. Penrose wrote a book about in a way, the limits of the mind. And one of the questions that he was asking if computer could beat the mind. This is a little bit also more pop science. But very recently, well, in 2017, well, indeed, some of the papers were former to 2017. Terence Tao asked also about if one could construct a fluid computer. And his motivation came from trying to find a counterexample to the Navier-Stokes conjecture. Okay, this was his original motivation. And indeed, he found a blow-up of the Navier-Stokes, but not really the Navier-Stokes equation, but an average version of the Navier-Stokes. And this was paving the way to asking this question. I'll give more details about this. Indeed, if we want to connect, indeed, to formulate this more properly, rather than talking about books which talk about aliens, we could ask if the complexity of fluid is enough to simulate any Turing machine. And if we have to talk about Turing machine, we are talking about somebody who was breaking the Enigma code. And this is excerpt from the film, The Imitation Life.
That's what you're working on. But you also haven't got anywhere with it. If you had, you wouldn't be hiring cryptographers out of university. You need me a lot more than I need you. I like solving problems, Commander. And Enigma is the most difficult problem in the world. No, Enigma isn't difficult, it's impossible. The Americans, the Russians, the French, the Germans, everyone thinks Enigma is unbreakable. Good. Let me try, and we'll know for sure, won't we?
Okay, so in this, well, now I don't see the full screen, but in this, well, I put here an excerpt of this is exactly what you don't do in an interview. This is an excerpt from the interview of the imitation game of the film. And of course, this is what you usually don't do in an interview, okay? To say, oh, you need me more than I need you. You don't have this kind of way to sell yourself. But well, here, let's say they want to, in this film to sell the product, of mathematician, and Alan Turing says, good, let me try and we'll know for sure, won't we? So with this sentence, let's say, well, this is inside the film, and he was known for breaking the Enigma code, but we could say with the same attitude, let me try and we'll know for sure, he was trying to answer a question, which is, can you find a supercomputer that knows that any computer or any program on the world will stop or not? And this was an open question also related to logics in computability theory, okay, which is called the halting problem. The halting problem is the problem of determining from a description of an arbitrary computer program and an input whether the program will finish running, so will reach the halting state, or it will continue to run forever. And Turing proved in 36 that the halting problem is undecidable. So this means that it's impossible, okay, that a general algorithm to solve the halting problem for all possible program input pairs cannot exist. So it's very important to point out that this does not refer to a particular program or computer, but to any arbitrary one. So that's an important piece of information. And this is a theorem that I will use, indeed, to say that it's undecidable to know whether these ducks will show up, we're going to show up in Alaska or not. And indeed, the proof of the halting problem is a very simple proof. Well, I took this from YouTube, from Computer File, which is very nice. And well, indeed, the proof was by contradiction. Let's assume that such a machine exists. Okay, so this is a picture that wants to think if we want to find such a machine, we should need to test all the possible machines on the world. This is a picture of all the possible machines of the world, which of course it's not realistic. But let's think of a program or a machine like a black box in such a way that you give it an input and it gives you an output, a yes or no output, for instance. So now the question that let's assume that we have such a program or such an algorithm or such a supercomputer, which let's say that answers the question, does a certain arbitrary program P hold with a certain input? Okay, let's assume that such a machine exists, and this is what we call the Turing black box, this supercomputer. Then Turing, what he did was, okay, if we have such a machine, okay, that it has a yes/no answer to the halting question, then we can always tune it, okay, in such a way that we can just tune it, we can just add some extra bit of information in such a way that it changed the outcome. So if the program was to stop, okay, then we make it loop forever. And if it doesn't stop, then we make it stop, right? We can do this if we assume that such a concrete machine exists, okay? And then if we have such a super machine, then we can feed it with any input. So the idea of Turing is, okay, if such a machine exists, we have a contradiction, because if we feed the machine with itself as program and as input, okay, then when it has to stop, it doesn't. When it has to hold, it doesn't hold because of this tuning, and when it doesn't hold, it holds. So there is a contradiction. It's a paradox. And why such a paradox makes sense? Because the big problem is to assume that you can construct this initial machine, because once you can construct, you can tune it. Okay, so that was the proof of Turing of the fact that the halting problem is undecided. And okay, this is what I need to know a little bit about Turing. And now let's say this is the formal beginning of the formal talk. So essentially a summary. In 1991, Moore was asking if hydrodynamics is capable of performing computations. These little 29,000 rubber ducks were lost in 92. And then in 2007, just one rubber duck showed up in Scotland. Then in 2017, Tao was asking about universality of Euler flows. Indeed, he was asking universality of Euler flows, which the question is, are Euler flows universal in the sense that can we embed any dynamical system as an Euler flow? Of course, I need to introduce what is an Euler flow and what do I mean by embed. I'm going to do it. And this was related to the Navier-Stokes. I will show in a couple of slides why. And then indeed, what was quite unpredictable is how we started to work on this. Indeed, we were working on something else with my student Robert Cardona and Daniel Peralta Salas. We were working on some problem in contact geometry with singularities. And then what happened is that this was, Tao asked this in 2017, but I think it was in 2018 that at that moment it's pre-pandemics. I was in a train. Coming back from Madrid, and I was on Twitter, and then I saw that somebody was referring to this question by Tao, and then I started to think that what we had done with Daniel, which was also to connect contact geometry and fluid dynamics with these manifolds with boundary indeed that had some singularities, if these ideas could be used to answer this question, if we could translate the question by Tao into a question in contact geometry. Indeed, this was quite we were just thinking of that. And then we started to work on this. And then well, first we did a construction of universality. And then not only we could prove that it was that Euler flows are universal, indeed steady Euler flows, so a particular type, the Beltrami fields, which all these I will introduce. These are a particular type of Euler flows. And then we could indeed produce, this was yielding, I mean, we will see in a minute why Tao was interested in these questions of universality and how this is connected to Navier-Stokes equations, that in order to achieve, let's say, a counterexample for the Navier-Stokes equations, he wanted to have, you know, a way to test a lot of initial conditions on Navier-Stokes. And a way to do it, he wanted these conditions to have some right symmetry conditions. This is related to his counterexample on the average model of the Navier-Stokes equation. And he wanted essentially to have a kind of generator of counterexamples. Mathematically, this idea of generator of counterexample can be translated as having something which is called Turing complete Euler flows, which in a way is a way to associate this idea of having a Turing machine with the idea of having a dynamical system. And in such a way that moving along the trajectories of a dynamic of a flow of a vector field of a dynamical system is equivalent to running a Turing machine. That's a little bit the idea. And then the notion of Turing complete is requiring that there exists a universal Turing machine. So this condition of Turing completeness in a way allows you to test a lot of initial conditions to try to find this counterexample of Navier-Stokes. So indeed, in order for this Turing completeness to be, in order to be able to apply these constructions of Turing completeness to the initial idea of Tao, we would need to do it in dimension 3. What happened from our universality proof that uses contact geometry is that we had to go to very high dimensions. And then we were obtaining construction of Turing complete in dimension 17 in a sphere of dimension 17. Then what happened is that also pre-pandemics, just pre-pandemics, in November 2019, I was giving a talk in Zurich in the analysis seminar about these universality results. I was very happy because I thought it was, of course, we had been working on it very, very intensively, and I thought it was a nice construction. But then the people in analysis said, what about dimension 3? So we came later with a construction in dimension 3. So we got to this construction in dimension 3, which is what I will explain today, from first studying the universality problem that Tao had asked. And of course, this universality problem is also related to the Navier-Stokes counterexample, because in a way you want to test universal examples. So in a way, you want to have this good property of Turing completeness on something which is quite universal. And this is why it was worthwhile to prove that Euler flows are universal. So indeed, these two questions are related. And well, later we came, of course, this construction, which uses this mirror between geometry and fluid dynamics, works for a specific type of Euler equations, of Euler solutions, which are stationary ones or steady Euler flows. And then the natural question is, do you have a construction of Turing complete Euler flows, which depend on time? And we were able to do this, but in higher dimension. I don't think I have time to explain this. And in all these constructions that I will explain today, it's very important that we are deforming the metric. There is a metric associated to the problem. I will give definitions, proper definitions, and we are playing with deforming the metric. And in this mirror, deforming the metric on one side that you don't see if you are working with Euler flows, because you don't even think about a metric. But the standard Euler equations would correspond to the Euclidean metric. But if you change the metric on this fluid part, this is equivalent to changing a geometrical structure here, which is a contact structure. So our game was really to change the metric. So a natural question, if you want this to be useful to produce some kind of counterexample to the Navier-Stokes equation, what would be nice is to be able to do it as Beltrami. I mean, to get a construction which is Euclidean, okay? And this is something we did very recently in November. but I think I have no way going to be able to explain anything. But of course, I want to thank my collaborators because I wouldn't be here without them, and we wouldn't be able, I think, to prove this without the force of joint collaboration. I learned a lot from them, including my student, Robert Cardona, who started a thesis with me about integrable systems, and then one day he was working with Turing machines, right? So essentially he did like 2 or 3 theses in one. And Robert Cardona and Daniel Peralta Salas, who is an expert in Beltrami fields and fluid dynamics, and Fran Presas, who is an expert in contact geometry. So a little bit the message is that if you put enough diverse people inside a room, maybe interesting things can happen. So what I'm going to explain mainly is this construction in dimension 3, but I'll revise a little bit this idea of universality. So I'm going to introduce, I was using the expression Euler flow, so let me now give some precise definitions. When I say Euler equations, okay, first I mean we can think of classical Euler equations, which would be these equations. These equations, I can write them exactly using the language of vector calculus, okay? But the interesting thing is that these equations, I can also think they are associated to a metric. And the metric which is associated to the classical Euler equations is the Euclidean metric. And with the Euclidean metric, this operation here, I can look it as a covariant derivative, okay? So I can say that Euler equations make sense for any Riemannian manifold. One could be a bit allergic to this idea, right? Because if we think about the movement of the little ducks, we want to think about physical things that happen in real world with a standard Euclidean metric. But on the other hand, we know that, I mean, many problems in physics are indeed need other kind of metrics to be described. So it's not so strange to look at Euler equations with a different metric. And with a different metric, we can generalize these equations just by replacing this gadget here, but the covariant derivative, okay? And the covariant derivative is, of course, associated to the metric. And here we take the gradient of the pressure. And these equations are equations of evolution. These equations here have the divergence. We have these equations, and the divergence is 0. And usually we take some initial condition. And what are the unknowns? Okay, this is a PDE, and the unknowns are the velocity of the fluid and the pressure. Okay, and well, these equations, if I use a metric, I write them in which way? I just replace this product here with a gradient, just with a covariant derivative, because this coincides with the covariant derivative in the Euclidean case. Okay, so I want to think of of Euler equations in this more general scenario of general metric, and changing the metric gives me the freedom then when I cross this mirror to change the contact structure, which is indeed what we need to achieve the proof, is to deform this contact structure. So if we deform the contact structure, this will correspond to the form of the metric. And well, as always in mathematics, if we want to consider the solutions to one equation, we are going to start with the easiest case. And the easiest case is going to be, okay, let's put us in the possible easiest case, the case in which the velocity doesn't depend on time. This is what we call steady or stationary Euler equations. And then then the first term disappears, okay? And I can write it like this, okay? And well, of course, Euler equations are what they are. They are like this. These are stationary Euler equations. But sometimes, depending on how you look at them, with which glasses you look at them, you can understand better things. So one thing you can do is to dualize these equations with the help of this metric, okay? I just consider the metric, okay? And then a vector field becomes a one form just using this duality. I just use a duality, and then an equation that implies vector fields become an equation that implies differential forms. And maybe I am one of the people in geometry who like differential forms. That's good. So then I can try to play with these forms. Okay. Maybe I like with Professor Cornea, who will also like to think of differential forms. Okay. So these equations in the language of differential forms are written like this. So this dualized, it means that I can dualize this equation, okay? And then I get just the contraction of the vector field with the differential of alpha, where alpha is a dual to x, is an exact one form. And this exact one form, indeed, it's the differential of the Bernoulli function. And the Bernoulli function depends on the pressure and depends on your metric. The divergence equation, I can look at it just by saying that the form contracting, this is, I could do it in higher dimensions, but let me think in dimension 3. Okay, that the contraction of the volume with the velocity, it's closed, it's a closed. Okay, so well, this has some advantages because if we have a one form, we usually want to compute the differential if we are used to working with forms. And this is going to be a tricky point because we will see that this form has some interesting properties, this alpha. But before that, let me introduce Beltrami fields. Beltrami fields are vector fields whose rotational is proportional to itself. Okay, and they satisfy the condition that the divergence is 0. Okay, in dimension 3, or I could say that Beltrami fields satisfy this condition in general. And what they satisfy is that they are solutions to the stationary Euler equation. Okay.
Excuse me, can you say what is mu in this line?
Yeah, this is the volume form that is compatible with the metric.
Thank you.
Okay. Yeah. Thank you. Yeah, because I didn't write mu. Okay, so Beltrami fields are going to be main characters of this talk. So let me give a couple of counterexamples. So I could consider the Hopf fields. These are examples of Beltrami fields on the 3 sphere. And if I'm one of these persons who likes perturbation theory and KAM theory, the ABC flows are very popular in the study of chaos. And ABC flows, which are the solution to this differential equation on a 3 torus, are Beltrami. Okay, so these would be examples of Beltrami fields on compact manifolds. So let's go back to the question of tau, and let me explain a little bit the Navier-Stokes equation conjecture. Well, you know that in the Millennium List we have indeed all these problems, and only the Poincaré conjecture has been solved. Okay, and well, one could try the Hodge, but okay, today maybe we try to look at Navier-Stokes equation. So Navier-Stokes equation is this equation here, which is it looks very much to the Euler one. The Euler one would correspond to this first term, and we have some extra terms, and these extra terms correspond to the information given by the fact that the fluid has some viscosity. Okay, and then we could also consider an external force, and we could think of these external forms as a kind of control in the problem. I mean, when one looks at this problem the first time, you think, oh, but you can vary this function, this external force that you have here. Yes, but then this is the Navier-Stokes equation, and then what could give you $1 million? $1 million would be to solve one of these two questions. Either you prove existence or you prove blow-up of the Navier-Stokes. And what are the Navier-Stokes equations? Then these Navier-Stokes, if you write it down, they look like this. The divergence has to be 0. Okay, and then if you look at the description that Pfefferman did of this problem, which you have in the website of the Clay Foundation, then well, this I must say that this guy here is just the Laplacian, okay, and well, it tells you that if you have some initial conditions, you cannot take any kind of initial conditions. You need to have some kind of control. Okay, so not any crazy initial condition will work. You need to have these bounds. Okay, and also for this external force. So if you want to get $1 million, then you have to constrain yourself to these kind of functions. And you think these are kind of Schwarz type condition, and it's sort of tough, right? To if you sit down one afternoon, okay, today I'm going to find a counterexample. It looks like a difficult condition. Okay, and of course you need to require that the energy is finite. The energy would be this integral, and U is the solution. Okay, so this is what Pfefferman describes as solution, what one could say legal solution to the Navier-Stokes. Okay, and then what remains open is the problem of either existence as a smoothness of this solution or counterexample. Okay, and if you look at Pfefferman here, I'm just making a short short description of the problem, he was describing 3 situations, okay? He was describing the situation on R3, the situation on the 3 torus, and some situation with extra symmetry. But let's reduce ourselves to the case of R3. Then the problem, if you want to prove that it exists, you can assume that f is identically 0. Okay. But if you want to prove that you have blow up, you can choose any f as long as it satisfies this kind of decay. Okay. So this is a tricky problem, of course. This is why it's one of the problems on the list. But Tao was able to prove some blow up for what he called average Navier-Stokes equation. And the way he was doing it was by using some former construction by Pavlov, I forget the authors, which used some kind of dyadic model, okay? And you look at the paper, it's a long paper full of equations and full of iterations. And essentially what he's looking for is some initial conditions which have a lot of symmetry, essentially. So guided by this average Navier-Stokes counterexample, and with the idea of trying to apply the same kind or similar kind of ideas to the Navier-Stokes, the question is, who are going to be these initial conditions? Then a first test would be, okay, if you want to look at some solutions, let's look at Euler equations where the viscosity here, mu, Alexandra, is the viscosity, it's not the volume, okay? And you want that maybe to test it on a simpler case. So to test initial conditions which are of Euler type. So this took him to ask the following question: can any incompressible vector field be embedded as an Euler flow by increasing the dimension of the map? And this fits into his program of the blow up program, which in his question was, can I program these initial solutions? And program is to construct Turing complete fluid flows. And the motivation was to create some initial datum such that it's programmed to evolve as a rescaled version of itself. And this idea of rescaling is what took him to the idea of Turing. Okay, let me talk about universality in very simple terms, okay? And I'm going to think of it like in a metaphoric way. Like here we have 2 standard pictures that you could take if you come to Barcelona any day on December. That's the weather you find, okay? Well, I was a bit picky choosing, I confess. And if you go to Paris, of course, you're not going to find this Santa Claus like here skating, but okay, I had to force it. But of course, you can spot 7 differences. You can spot quite a lot of them. But if you are far away, if you are in the International Space Station, maybe you don't see the difference. So essentially, if I have a dynamical system, by increasing the dimension, maybe I can embed a look at this dynamical system from the distance as the solutions to Euler equations. So this is what universality brings me to. Now I need to talk about geometry, okay? When I was explaining the problem of Euler, I was explaining that I was considering these equations as a geometer, and I had a one form called alpha. And I told you, I'm tempted to compute the differential of this one form. This is because one is tempted to see if this one form is going to be contact, okay? And today I can't forget about symplectic geometry, though for, let's say for emotional reasons, I leave it here because I come from symplectic geometry. And contact geometry could be, let's say, the odd equivalent to symplectic geometry, where the geometry is associated to a one form. In symplectic, you have a 2 form. And this one form satisfies the condition that if I'm in dimension 3, okay, the condition is very simple to describe. I just look at the kernel of alpha and I impose that this gives me a distribution, but this distribution is non-integrable. The non-integrability of distribution, I can describe it as the one form alpha satisfying this condition. Alpha wedge the alpha defines a volume form, okay, if I'm in dimension 3. If I'm in higher dimension, alpha wedge the alpha n is a volume form. So it never vanishes. And that's the condition of equivalent to this non-integrability. And the picture here is a picture of the kernel at each point of alpha. Well, in contact geometry, if I compare it to Riemannian geometry, one could be a bit disappointed, also symplectic geometry, because locally any contact manifold looks the same. and the only invariant is the dimension. Why? Because you can always find locally your contact structure can be seen as the kernel of this one form. Okay, and in contact geometry, an important vector field, as in symplectic geometry, is the Hamiltonian vector field, is the Reeb vector field. I could also talk about Hamiltonian dynamics, but today it's enough for me to talk about a specific class of Hamiltonian vector fields, which are called the Reeb vector fields, which satisfy this condition, that they are in the kernel of the differential of alpha, okay? And then I have a whole, from this definition, I have a whole one direction, and then I need to choose one, okay? And instead of using a metric and normalize it, I use alpha, and I impose the condition that alpha of R equal 1. And the solution to this equation, there is a unique vector field, which is called the Reeb vector field, okay? And in dynamics, it's very important to consider consider properties of this vector field. Okay, an example of contact structure. This is a beautiful picture which was done by Robert Geist, which is a picture which wants to picture, okay, all these planes that at each point that you cannot find a submanifold such that the tangent space to this submanifold equals the kernel of alpha. Okay, and this will be an exercise for our students. Okay, I take alpha in Darboux form. Alpha is the differential of z minus y dx. Okay, and then the kernel is described by these two vector fields. It's an exercise for our students to check that this distribution is not integral. And by dualizing it, this is equivalent to d alpha wedge d alpha non-zero. And this is equivalent to, indeed, we compute it, and alpha wedge d alpha is just a standard volume form. Okay, so this is an example. And contact geometry, indeed, it's also funny for day-to-day life. It explains why it's so hard to park a car. Indeed, it's a theorem by M.E. Murphy that if you have a car of length L, you can parallel park it in a space of L plus epsilon. This is what theory tells you, that for any epsilon, you can park it. The truth is that, okay, try to park it for any epsilon, but you can prove this using contact geometry. This is a nice application, and you can find this in some notes by M.E. Murphy. Let's look at Hopf fibration, okay? This is an example that I said very quickly. I was saying that the Hopf vector fields are example of Beltrami vector fields, but indeed, it's also an exercise that we could leave for our students, that if I consider the sphere and I represent it in complex coordinates, okay, then I take this alpha, okay, then the orbits of the Reeb vector field indeed coincide, okay, give me this Hopf fibration, okay, and here the classical mem, wait, it's all Hopf fibration, always has been. Okay, is this a coincidence? Maybe it's a coincidence that the vector field is at the same time Beltrami and Reeb vector field, but it's not a coincidence. It's a theorem. The theorem is a little bit more complicated. The theorem tells you that this alpha that I was playing with some slides ago, okay, in terms of alpha, which is the contraction of the metric with the solution to the stationary Euler equations, and mu is the volume form, okay, then the stationary Euler equations, I could write it like this, okay, and then, well, the theorem by Endner and Geist is that there is a one-to-one correspondence between Beltrami fields and Reeb vector fields. And this correspondence is up to reparametrization. That is to say, if I consider alpha the construction of the metric with this vector field, then this one form is a contact structure. Okay, but the Reeb vector field maybe is not exactly the Beltrami field. It could happen that maybe it's not exactly that field, but after reparametrization, they are the same. Okay, that's what the result says, and this is exactly what we were proving with Robert and Daniel Peralta Salas when we at the beginning, when we saw this question by Tao. This is exactly the kind of result we were proving. We were extending indeed their theorem to singular contact structures. And indeed, this works in higher dimensions, this correspondence. So this correspondence gives you a magic mirror to go from geometry to fluid dynamics, okay? Or maybe if you want from Endner to Geist, depending on what you want to become. Okay, So this magic mirror indeed was used at the beginning by Edner and Grist to prove existence of periodic orbits of Beltrami vector field, for Beltrami vector fields. And the way to prove it is that, well, in contact geometry, a famous conjecture called the Weinstein conjecture tells you, which was proved for 3-dimensional manifolds later than their paper, indeed. So the applications they give is only for the 3-sphere, which was proved by Hofer. It tells you the Weinstein conjecture, it tells you that any Reeb vector field, okay, on a compact manifold admits at least one periodic orbit. That's the statement. And then you can, as you know that this holds in contact geometry, then as a direct application, you have periodic fields for Beltrami vector fields whenever the Weinstein conjecture is satisfied, which is also in other cases. Another beautiful gadget you have in contact geometry is the H principle. And the H principle allows you to prove, this is, I will not explain the details, some Reeb embedding theorem. As an application, this gives you the universality. And a very basic construction, which is the one that gives the correspondence in dimension 3, allows you to prove that the Reeb suspension of area preserving diffeomorphism of the disk, okay, gives you a universal Turing machine. Now, what I'm going to do is to describe very briefly how we did this. So the question, let me go back to the question of tau. The question of tau is, can any incompressible vector field be embedded as an Euler flow in higher dimensions? That is the question of tau. Okay. Then here we use this magic mirror. Then this question about incompressible vector fields, it's a question, if I think of it in the case of Beltrami vector field, is a question that I can translate as a question on Reeb vector fields. So we just translate the question of tau. Can we realize a vector field on a manifold N as a Reeb vector field on a bigger compact contact manifold? That's the question. Of course, there are conditions. First day we started to work on this, we were playing with, you know, the typical first errors you do when you want to find a proof. But one thing we realized is that you need that this vector field is geodesible on M. And this condition on geodesibility, I recall it, okay, is a condition that usually we explain to our undergraduate students, is that a geodesible vector field is a vector field for which there exists a Riemannian metric, such as the orbits are geodesics of unit length. Okay, and indeed it was Hermann Gluck, who proved that this condition is equivalent to the existence of a one-form alpha, such that alpha of x equals 1 and the contraction of x with the differential of alpha equals 0. And then you are going to say, wait a minute, this is exactly the definition that you gave us of Reeb vector field. Let me go back to this first mirror. This is exactly the definition of Reeb vector field. So this is trivial then, the question you're asking. No, but it's tricky. Gluck tells you that there exists an alpha, but doesn't tell you that alpha is contact, okay? So the question that we need to address is, if given a one-form alpha that satisfies such a condition, we can deform it to a contact form. That is the question in our language. So the first question is if this condition is sufficient, and the second question is, okay, geodesical vector fields, I don't want to hear about them. How complicated is to get a geodesical vector field? Let me answer the simplest question, which is question 2. It's easy to check that if your initial, you take your dynamics and you assume your dynamics is periodic. If the dynamics is not periodic, you can work in a similar way, but then you obtain a construction which is not on a compact manifold. So today I'm going to consider the case of periodic dynamics. Then if you take any periodic vector field, then it's very simple to say that you do the suspension game. So you just push forward this vector field on the product with S1, and then it's very easy to see that, okay, your initial vector field, maybe it's not geodesical on M, but now you consider the new vector field, which is the push forward, which is this OY, and you consider as manifold N times S1, okay? And then this vector, this is geodesical. Why? Because I just use the definition of Gluck, and I just need to find a one form which satisfies, and here I take just the differential of theta, which satisfies this condition for the push forward vector field. Okay, so the answer is to the question, it's not difficult. Just by increasing one dimension, I can think of that the geodesimal condition is not a very restricted condition. Okay, and because the universality problem implies increasing the dimension, then this is a reasonable assumption. And the second thing, and the other question, is this condition sufficient? Is the question if I can deform any of these forms into a contact form. And this, the inspiration of the kind of proof we did, comes from a paper by Borman, Eliasberg, and Murphy, where they prove that any almost contact closed manifold is contact. Indeed, now it's like, this is a colloquium, I shouldn't talk about what is almost contact, but I can say that in dimension 3, everyone knew that any manifold was contact. And the natural thing is what happens in higher dimension. So in higher dimension, there is let's say a condition which is called almost contact that you require, which is of algebraic nature, I could say. Okay, you can essentially find this condition just by doing some diagram chasing on your manifold. Okay, so indeed they prove that this almost contact condition would be a formal condition in the language of H principle. And what is the H principle? The H principle essentially can be explained in 3 steps, as everything in life. The first thing is that in life you have a goal, and this goal can be, for instance, you want to solve an equation. And well, usually in life you have a goal and you achieve a semi-goal, which is, okay, I wanted to solve a certain equation, but instead I solved the linearized one, or maybe the formal equation. And then, as always in life, you need a miracle, right? Because you solved your linearized equation, but you want to solve the initial equation. So the miracle, and this is given thanks to the H principle, is that you can sometimes deform, using an homotopy, a formal solution to a honest solution. Okay, so a honest solution will be a solution of your initial equation. And this idea, the H principle, is what we use. Essentially, we have an alpha that satisfies the condition of Hermann group because it's geodesic. And we want to deform it, okay, to an alpha that is contact. So it's exactly the same kind of problem. And I will not explain the details because it's boring, but I can tell you that we could prove, and it's important to know what is the dimension, that if we start with a manifold of dimension n, where we have certain dynamics, and I don't need to assume that the vector field is geodesimal anymore, because I'm already playing with this game of promoting a vector field to a geodesimal vector field. So essentially, if I have any dynamics on a manifold of dimension n, I can always embed these dynamics as a Beltrami field in dimension, and then the dimension is one of these 2 dimensions. Okay, this is what we proved. We didn't prove if this is sharp. Okay, but we could prove that we could go to 3 dimension of n plus 5, or 3 dimension of n plus 6, depending on which one of these 2 numbers is odd. Because we need, our construction uses the mirror, so it uses this contact geometry, which only makes sense in all dimensions. Okay, so what we could prove is that the answer to the question of tau is yes. Okay, we can embed any dynamics as Euler flows, indeed as steady solutions of the Euler equations. And then the difference is that, what can we say about the metric? Our construction allows us to say that the metric is exactly we can assume that it's the Euclidean metric outside some toroidal set in which you cannot assume anything, essentially. And the proof is, by using the suspension trick, is what I wrote here. We just translated it into a problem of the H principle in contact geometry. And the inspiration and tools is, well, I could say just developing what Borman, Eliasberg, and Murphy did, but this just is a lot of work. It's a long paper. Okay, now it's time to talk about the 3-dimensional case. I'm sorry, because I was a bit slow. And I need to talk about Turing completeness. Okay, so I'm going to think that a vector field is Turing complete if it can simulate any Turing machine. Okay, and then this is equivalent to, if we go back to this halting problem, this is equivalent to the halting of any Turing machine with an even input is equivalent to a certain trajectory of the field entering into a certain open set. Okay, I have a precise definition, but I think I will skip it. So just think of this picture. We think that essentially when we talk about, we need to associate a Turing machine to a flow. Okay, and let's say this is done with an encoding, where the encoding associates following the flow of the trajectory. Okay, then we say that it has this property of Turing complete if it can simulate any Turing machine. Okay, so then one thing we could do was to use our game of promotion of constructions to geodesical vector fields using some old construction of tau in dimension 4. So essentially, as a corollary of the universality theorem, we could get a construction of a sphere of dimension 17. But of course, if you give a talk in front of analysis of people working in analysis, they say, this is dimension 17. Give me something in dimension 3. So can we do this better? And the answer is yes. We could prove that there exists a normalizable flow in dimension 3, which is Turing complete. Okay, and the metric, what we could say is that the metric is the standard one outside the complement or on the complement of an embedded solid torus. And an interesting consequence of the halting problem that I explained before is that there exists undecidable fluid particle paths in dimension 3. This would explain why these ducks didn't show up in Alaska. Okay, this would just as a consequence, because the definition of Turing completeness, what it does for you is to connect the notion of following the flow with the notion of halting problem. Okay, because it says that the definition that I'm going to take, I mean, there is a formal definition, is the halting of any Turing machine is equivalent to the flow entering a certain open set. Okay, and because the halting problem is undecidable, then certain fluid paths are going to be undecidable. Okay, so essentially what it proves is that there is no algorithm to decide whether a trajectory will enter an open set or not in finite. That's exactly the concept. And then it's very important to say that this doesn't give us the finite time blowup of Navier-Stokes. Otherwise, we would have read it somewhere. And well, it doesn't give this this blow-up solution, because if we take these solutions of initial conditions, we could indeed find what is the solution. Okay, what is the evolution of these initial conditions? And the evolution of this initial condition is as such. So it exists for all time. It doesn't blow up. And indeed, it's, if you want to ask the question if it's Turing complete, because of this exponential decay, then it can just simulate a finite number of steps of a Turing machine. So it's not good. Okay. So how do I have to think of a Turing machine? I want to think of a Turing machine as this long tape. How much time I have?
Officially 2 minutes, but you can certainly take a bit more.
Okay, I'll try to make it short. Thank you. So let me say, like, the image of Turing machine that we have is exactly this image. We have a long tape, but we need to think as a Turing machine as a printer, where we have some states and we are printing on a tape. Okay, and indeed the states. So this is why we can think that a Turing machine is the collection of states. And among these states, there are two important states: the initial states, the Q0, and the halting state. Okay, and these why they are important, because in the user guide that you get when you buy a Turing machine, inside the user guide you have the instructions, and it tells you how it works. It tells you, look, if you take a state and it's the halting state, then it's going to stop. Otherwise, the rule you need to follow is that, of course, one element of this halting state is the transition function. The transition function, it tells you how you need to print on this tape. Okay, if you need to go on the left or if you need to go on the right. Okay, and well, sigma is the alpha, and this -1, 0, or 1 tells you if you go to the right, to the left, or you stay on the same place. Example: imagine that you have this instruction, this transition function. We have this tape full of zeros, and we say, well, the transition function that is q to q prime, and the instruction you have is this one. This means that you need to, okay, this +1 it is that the tape moves to the right, but this means that you need to move to the left for the tape to move to the right. And then you need to replace the 0 by the 1 and move. Maybe it's good to see a video of this, exactly of this operation. Here you just have this operation, you replace the 0 and 1, and then you move. You are moving to the right. You have this +1. This is why you have this, this is why the tape is moving to the left. The printer is moving to the other direction. And if you don't like this tape image, you can think of Conway's game of life, which is an automaton. And indeed, it was von Neumann who proved that any Turing machine, well, you can think that you can associate a cellular automaton. Okay, so Conway's game of life is essentially a game with no players. So you can think it's a boring game because you have some cells and there is some rules of survival and death. Okay, it's a boring game unless you play this game on the torus. Then it's not so boring. Okay, you have some instructions and it goes forever. Indeed, it's a dynamical system, right? I mean, because you have some evolution according to some rules, and this evolution here on the torus of survival and death is exactly what gives you the dynamical system. Okay, so okay, now that we saw this system, let's look at another dynamical system, and this will put me close to the end. This is another this is a nice. I must confess that I took this from YouTube from Robert Grice, who is, besides a mathematician, a wonderful illustrator. And this is an illustrator of the Cantor set. So essentially you are throwing away, you have the interval and you are throwing away the middle, the third, you divide it in 3 parts and you throw the middle of it. You throw it down the middle of it. And you do this as a recursion. You can think that, well, this is an iterative process. This is an example, very simple example of fractal. And indeed, this is a dynamical system. Okay. Well, now I was too quick. 1 second. Okay. So indeed, this example of fractal and this example of Cantor set reconciles again dynamical systems with Turing machines. Okay. Indeed, Moore generalized the notion of shift, okay, to simulate any Turing machine. And he proved that you can associate to a Turing machine what is called a generalized shift. And a beautiful thing of Moore is that generalized shifts are always conjugated to maps on the square Cantor set. So this example of the Cantor set would be a toy example for a Turing machine. You just take a product, okay, and then it's equivalent to take a Turing machine. It's equivalent to take a mapping between 2 square Cantor sets. And then the way to associate the Turing machine or the encoding, it's very simple if you have a Cantor set. Just take the ternary span, and this gives you just take the positive on the x-axis and the negative on the y-axis. This constructs for you the encoding of the Turing machine. Indeed, well, this is the formal definition that I gave before. Okay, but well, I mean, it's a bit boring to look at this definition, but I'm going to present as a black box a very nice construction of exactly this construction of Moore. So Moore proved that any Turing machine, you can associate this mapping between the square Cantor set. So the only thing we did with Robert Cardona, Daniel Peralta, and Fran Presas was to extend his construction, which was defined on the square Cantor set inside this square. We could extend his construction to get an area preserving diffeomorphism of the disk. Okay, and what is nice about this, I'm going to use exactly the same idea of suspension. If you have an area preserving this diffeomorphism of the disk, okay, and then this diffeomorphism of the disk, we make it be like the identity is close to the boundary. This is because we want to extend it afterwards. Once you have this property, it's easy to check that this diffeomorphism can be preserved as the time one map of a red vector. And in order to, and the idea of the proof is exactly the same idea of the suspension. What it does for you is to prove the theorem. What I have just said is take an area preserving diffeomorphism of the disk. This diffeomorphism is an extension of the mapping of the Cantor set that gives you the Turing machine. Okay, the fact that this diffeomorphism is area preserving allows you to prove that this diffeomorphism is the time one map of a Reeb vector field. Okay. And because of this construction that is close to the identity to the boundary, we can play some Moser tricks with the contact form. Indeed, essentially, this is a picture. We have a Turing machine in 2 dimensions, and this allows you to make a 3-dimensional construction of a vector field. This vector field is a Reeb vector field. Okay. Therefore, this vector field, because it's a Reeb vector field, we just cross the mirror. It's going to give you a Beltrami field. So in particular, solutions to the Euler equations, steady solutions to the Euler equations. Okay. This is exactly the construction we did. The question is, okay, you start with something which is Turing complete. Why is this thing Turing complete? You are just promoting, okay, with this idea of suspension, and the suspension is holonomic. So you have a Turing complete construction. So this, and with this I finish my talk. This proves the theorem, the construction in dimension 3, which is what Alexander asked me to explain, of the proof. So the idea of the proof is work as an extension of a Turing complete diffeomorphism, which is area preserving. This, you can extend it to the time one map of a Reeb vector field. Okay. And this proves what I call theorem 3. And well, I mean, I've got something else, but with this, I'm going to finish my talk. Thanks for your attention.
Thanks you very much for this very nice talk, Eva.
Thank you.
Yeah.
I'm sorry to go over time.
It's okay. We have time for questions now. So please, if you have a question, you can relay it in the chat or just unmute yourself and ask your question.
Hello.
Hello.
Lovely talk. Thank you. Could I just ask you to say a word about the encoding when you move between dynamical system to Turing machine?
Yeah, I mean, this is tricky. This is tricky. That's a very good question, because I have been selling, I mean, there is not a one-to-one correspondence in this construction. We make a specific encoding that follows the flow. Okay. Is this encoding unique? It's not. So there is, let's say, I am explaining things with easy words, but it's a bit more tricky. We make a specific encoding. In our construction, in the Turing machine construction that we do in dimension 3, this is very simple to explain, because we reconstruct, let's say, the reconstruction from the encoding or from the Turing machine to the vector field follows exactly what Cris Moore did in the past. So there the encoding, in his case, it's associated to the Cantor set, is given by the ternary expand. And then what we do is to extend this to a diffeomorphism. So our construction uses an extension of a diffeomorphism, but it's not unique, of course. Any extension of the diffeomorphism is going to work, and it's going to be a different construction, therefore a different encoding. So to make it short, I didn't explain one has to be very accurate about the encoding and the dynamical system. And given, let's say, given one dynamical system, given the flow of a vector field, there are many possible encodings for that. And that's a little bit the tricky part of the story. Thanks for the question.
Thank you.
I mean, I could explain this, but this wouldn't be a colloquial talk. This would be boring.
Does anyone else have a question or comment? I have a simple, or maybe illustrating my lack of understanding one myself. So the Riemannian metrics that show up, do they play the role of modeling the geometry of the space where the flow is taking place, or do they have a different physical interpretation?
Yeah. So the physical interpretation is exactly, we are like changing the geometry of our space. Like, let's say the Euler equations would correspond to the movement of the fluid, assuming that the classical Euler equations would be exactly the Riemannian ones with the Euclidean metric. And then let's say that when we say physical equations, are exactly the Euler equations correspond to the Riemannian metric with the Euclidean, in the Euclidean case. But let's say if we change this metric, in a way this would correspond physically, how could I say it? You know, you change just in one part of your space. Our construction indeed just changes the metric on a neighborhood of the image of this embedding. Indeed, in the three-dimensional case, on a torus, on a dense torus, on a solid torus. This solid torus can be very small. It's a ring. Okay, it's just a small ring on the big space where you change. You could think, I mean, physical interpretation, I could say that physically this wouldn't be physical, but you can always find physical interpretation for another Riemannian case. I mean, yeah, it would be cool, okay, if some physicists would tell me that, you know, in some black hole, if you look at these equations, then you get non-standard Riemannian. This would be cool. If I can find this, I will add it to the paper. Okay.
So in the context of the $1 million question, if you had to change the geometry, would you still win the money, or you have to do it for flat space?
Yeah, that's a tricky thing. You wouldn't get 1 million unless you are able to take this ring where you don't have the standard metric and make some limiting process that converges. Okay. Well, let's say we were not in this game to prove a counterexample to the Navier-Stokes, just to be, I mean, we were working on something else, but it's fun, right? So the idea occurred to us. Indeed, I can explain, well, this is recorded and will be in YouTube, but I will say this, I hope my collaborators are not angry with me, that in December, my last trip was to Madrid to visit Daniel. And then we were in a meeting with Daniel, another collaborator, Angel, and Robert. Robert was connected in Zoom, and we were overexcited because we thought we had found a way to find a counterexample. Okay, and then the funny thing is that I went crazy. Oh, this gives us a counterexample. Let's assume that this blah blah. And then the guy, you know, Robert Cardona was on Zoom, and he was shouting, "No, guys, this is impossible. If this was as simple as this, Tao would have discovered this." And this is, let's say, the young guy. The young guy was saying, "No, stop, this will not work." But we were there for 3 hours, blah, blah, making out of equations. I went to sleep thinking, oh, we found a counterexample. And then the day after, we had to assume something had to be 1 and it had to be 0. Okay. And then coming back to your question on Riemannian metric, maybe by changing the Riemannian metric, you can find this counterexample easier. This I still cannot answer, but it's an interesting question. I mean, indeed, you get a lot of geometrical questions by looking at this. And indeed, right now, I mean, I put here some open problems, some things we have done, okay? Some things we are working on, but we are also working currently on understanding these embedding theorems of Tao from a geometrical point of view. And there are a lot of connections with quantization and a lot of connections with representation theory. So it's a rich theory for a geometry, okay? So I'm enjoying a lot. I mean, who could tell me that at my age, I could enjoy so much spending hours and hours making fake counterexamples. But so let's say it's tough, right? I don't know. I mean, it would be cool. I mean, what it's clear is our construction doesn't give this counterexample, but it's not the only construction. It's a construction that, I mean, you can ask many questions about the stability of this construction. I mean, we are trying to understand this, okay? But we are trying to understand this indeed already motivated from the dynamical point of view. But understanding this also has some implications in the program of Tao. So.
Thank you. Anyone else wants to ask something before we finish? If not, thank you again for this very nice talk. It was a pleasure to listen.